Can we detect mental depression with EEG signals? So the aim of the project is to build an AI model that can automatically tell the difference between individuals like with depression versus healthy controls without depression. And this should happen using psychological patterns extracted from EEG brain signals. The goal of the project is to develop an EEG-based depression detection system using WST, wavelet scattering transform features, and machine learning to improve classification accuracy. What is EEG? EEG stands for electroencephalogram. Using an EEG cap, you can measure the electrical activity happening inside your brain. EEG has already showed its usability in different applications like Alzheimer's, emotion recognition, neurodegenerative disorders, and etc. Background. So about EEG signals. EEG signals are groups of waves, and these waves are usually called delta, theta, alpha, beta, and gamma. And these frequencies change based on what's happening in your brain activity. So the existing challenges. Depression is a common mental health disorder, and it's usually diagnosed through clinical assessments. And discriminating the state of mental depression from healthy is highly challenging using only raw EEG signals. There is no need of advanced feature engineering techniques for EEG signals that a machine learning model can learn and accurately diagnose mental depression. So there's a description for MODMA. So MODMA is an open multimodal dataset made for mental disorder research, especially depression. And it provides real EEG recordings from clinically diagnosed depression patients and healthy patients. Data is usually available from 128 channel event-related potential recordings and the 128 channel resting state recordings. And this is the methodology. So first, EEG data acquisition, the first step. EEG signals from healthy controls in depression patients. This is the MODMA dataset. And methodology, so pre-processing, this is the second step. So we're filtering bandpass and artifact removal, re-referencing, and ePod segmentation. And the third step is wavelet scattering transform, also known as WST. Multi-scale time frequency decomposition, and first order scattering coefficients and second order scattering coefficients. And this is the third step. Feature extraction, the fourth step. Extracting WST coefficients per ePod, statistical and spectral descriptors, and construct ePod level feature vectors. This is the fourth step. Fifth step, subject level feature aggregation. Aggregate ePod features for each subject and compute statistical summary. So mean, standard deviation, median, and quartiles. And usually quartiles is if it's applicable. And this methodology, multi-feature fusion, this is the sixth step. You fuse WST features with complementary psychological descriptors and construct optimized subject-level feature vector. And training fold feature engineering. This is the seventh step. And it's usually performed only inside the training folds to avoid data leakage usually. So variance thresholding, mutual information ranking, top K feature selection, and standardization, Z-score. And the seventh step, optimized XGBoost classification. So in this, we use hypermeter optimization, like basin search and grid search, class balancing, subject-wise cross-validation. And for the ninth step, depression diagnostics, predict subject label, usually healthy versus depression, and performance evaluation, usually accuracy, sensitivity, specificity, precision, F1 score, ROC, AUC, balance, accuracy, and confusion metrics. For explainability analysis, we use SHAP feature importance, permutation importance, statistical significance, p-values, effect style, correlation analysis, top feature visualization, distributions, and heat maps. And ablation studies is the last step. So we remove WST features and without feature fusion usually with the different feature selection strategies, different classifiers, different wavelet orders. And these are the results and fold-wise accuracy of the method that we used. So there's a picture here. And 10-fold accuracy means the modal quizzes itself on the first 9 groups and then tests itself on the remaining 1 group, and it repeats the strategy 10 more times, and then it's just basically doing the 10-fold strategy. And this is the method-wise comparison graph. In the methods that we use are EEG pre-processing, wavelet scattering transform, feature classification, and modal evaluation. And the results for baseline. Saha's paper, handcrafted TFVP features with random cross-validation with accuracy of 92%. And then baseline with no leakage. So I found leakage in the baseline in Saha's research paper, so then I tried subject-wise validation, and this eliminates data leakage with results of 59% accuracy. And wavelet scattering features, WST, improve robust EEG classification with 94% accuracy. WST with no leakage. Stability selected WST ensemble with subject-wise validation with 56% accuracy. It gave 64%, but then it classified everyone with depression, so that's not really correct. And this is the results for baseline. This is the results for WST. And these are the results for the baseline with removed leakage. And this is just with removed leakage. And the conclusion that we reached is the proposed wavelet scattering transform with XGBoost achieved the best performance, reaching 94.14% accuracy. And it's outperformed all baseline methods and classifiers. Results were consistent across the 10-fold cross-validation, and it had low miscalculation rates. And that demonstrated that wavelet scattering features provide a more discriminative and robust representation for EEG-based depression detection than handcrafted temporal features. Thank you.